Hi, and welcome to this flipped instructional session. Today's instructional session is going to be the Unit 4 review in preparation for the Unit 4 test. This is Earth Science Semester A, and I am Mrs. Fessel. Let's get started. So first, the most important thing about this unit is its plate tectonics. This whole unit is about the theory of plate tectonics. The theory of plate tectonics states that the Earth's crust is broken into pieces called plates that move slowly across the Earth's surface. In this picture, you can see the little red arrows show what direction all of these different plates are moving in. So next we're going to talk about how we came to know about this theory. The person who came up with this theory was Alfred Wegener, and he had 4 pieces of evidence to support his theory of continental drift, what became the theory of plate tectonics. So first of all, up here, he noticed that the continents fit together like puzzle pieces, especially South America right here into the coast of Africa. Next, he saw ancient mountain ranges lined up, such as the Appalachian Mountains in North America line up with the mountain ranges throughout England and Scandinavia. Next, he saw fossils lined up. Fossils of animals that couldn't swim were found on opposite sides of the ocean, again, such as on the coasts of South America and Africa. And finally, glacier evidence. Places that are today near the equator and hot, such as India and Africa, have evidence of ancient glaciers. That tells us that they must have moved from their current location. So the supercontinent Pangaea has broken up over the past, I think, about 300 million years. So Pangaea started off as all of the continents connected together, broke into 2 continents called Laurasia and Gondwanaland, and then they continued to drift for the next 200 million years into their current locations. So the theory of continental drift also tells us that. So how are these plates moving? That's the big question that Alfred Wegener could not answer. That's why scientists did not originally accept Alfred's theory of continental drift, because he had no way to explain how the continents moved. Now, today, we have a theory of how they move, but he at the time did not. And that's what we're going to talk about next. So knowing how the continents move is based on the layers of the Earth. The crust is the outermost layer made of solid rock, followed next by the mantle, which is a superheated plastic-like rock, which is important to plate tectonics, followed by the outer core, which is liquid metal, and the inner core, which is solid metal. These layers of the Earth are what allow the plates to move. Specifically, the asthenosphere, which is part of the mantle, which, as you can see right here, is superheated rock that flows very, very slowly over millions of years. That is what the lithosphere, or the tectonic plates, ride on top of. So the lithosphere that I just mentioned is made up of 2 parts of the Earth, the crust and the top layer of the mantle, which are both solid. The asthenosphere, the plastic-like layer, is right underneath of it. So those forces of the convection currents are one thing that is responsible for plate motion. We're going to talk more about convection currents here in a minute. And the second thing that causes plate motion is gravity. Gravity pushes mid-ocean ridges down. In addition, it pulls the slabs of rock down into the Earth. And we're going to talk about both of those in more detail in a minute as well. So convection currents. The base of a convection current is rock at the bottom of the mantle heats up, becomes less dense, and rises. That's what you see happening to the red dots here. They spread apart, which makes them less dense. Then they hit the cool surface of the Earth right here. As they cool, they clump closer together, get heavier or more dense, and from there, they sink back down. So these convection currents, this cycle of heating, rising, cooling, and sinking, is one thing that moves the plates. because as the convection currents cycle, the plates move with them. All right, so all of these moving plates cause different types of boundaries. So the one thing that can happen is called a convergent boundary. A convergent boundary, as the base word converge would tell us right here, the base word converge, when two things converge, they come together. So in a convergent boundary, two plates move towards each other. So a couple different things can happen. If it's two continental plates, we get giant mountain ranges forming. This is how the Himalayan mountains formed, was from the Indian plate crashing into the Eurasian plate. We can also form volcanoes, trenches, and earthquakes. This more likely happens when an oceanic plate right here is going underneath a continental plate up here. First, the plate can melt right here, and that melted magma rises and forms a volcano. A trench forms right here because, as you can see, this little V shape forms as one plate plunges under the other, pulling it with it. And finally, as these two plates grind against each other, it can form earthquakes. So these are examples of what can happen when two plates come together or towards each other, which is a convergent boundary. The next boundary type is a divergent boundary. Diverge, like the word divide, means they're moving apart. If you divide a number, you're splitting it apart. So two plates move away from each other. So the biggest things that this forms as the plates move apart is mid-ocean ridges, such as the Mid-Atlantic Ridge, and volcanoes, because as this magma comes out of the crack here, it cools and forms volcanoes and this ridge of mountains. The last boundary type is a transform boundary. So in this case, two plates are grinding past each other in opposite directions. This creates a lot of earthquakes. A great example of this is the San Andreas Fault in California. As these two plates move past each other in opposite directions, it causes California to have lots and lots of earthquakes. All right, so the last thing we're going to review today is ocean floor geography. So there's different parts of the ocean floor that we can see because of plate tectonics. So the first one is the continental shelf. So the continental shelf is right here. It's this area of undersea land reaching just 200 meters, so not very far, out from the shoreline. So if you go swimming in the ocean, the continental shelf is what you are swimming on. Then we have the continental slope right here. As the name indicates, it is a slope, a steep drop off down into the ocean. So this is not where you're going to be swimming. And then which is the relatively steeply sloping undersea land extending from the outer edge of the continental shelf. Finally, we have the continental rise. So this is a gentle rise that meets up with the continental slope. So this is a region of gentle slope between the continental slope and the main ocean floor. So I always remember this because the continental rise, it rises up to meet the slope, which meets the continental shelf. Finally, we have our last few words. The abyssal plain. A plain means it's flat. So the abyssal plain is this flat expanse of ocean floor. So most of the ocean is made up of these abyssal plains. A seamount is a cone-shaped volcano. So you can see it right here. And as this volcano keeps erupting, if it does, it might break the surface of the ocean and actually become an island. But if the seamount gets eroded down and has a flat top, like right here, this is called a guyot. And then finally, as we talked about, when two plates meet, we can have a deep sea trench, which is a long, narrow depression in the ocean floor. So that's all the review we have today. Be sure to look for the flipped follow-up for the test coming up in your Class Connect schedule. And don't forget, if you took notes or if you watch this presentation again and take notes, you can submit those notes for up to 3 points of extra credit, which could definitely help out your grade. Thank you for watching, and I hope you have a great day. Bye.